We have studied and mastered Kirchhoff laws and the equation of radiative transfer. We have the deck of cards and we know the rules. It's time to play the game. Let us apply the equations of radiative transfer to the case of a star and understand how radiation is transported through a stellar atmosphere. So this shows the spectrum of the sun. You have the ultraviolet, visible, and the infrared. The three main features here are spectral lines, which are bound transitions, excitation or de-excitation between levels in the atoms and molecules. The Balmer jump, which is a bound-free transition when you are ionizing the atom hydrogen. And a continuum that is an example of free emission, Bremsstrahlung becoming black body. So let's understand in detail how radiation is being transported in the atmosphere of a star. For that, we're going to do the plane parallel approximation. Now let's understand what it means. Let's write the equation of radiative transfer in spherical coordinates. Because of the spherical symmetry of the problem, the depth is the coordinate where optical depth increases. And without loss of generality, we can align that with the z-axis. And the equation of radiative transfer involves a derivative with respect to the optical depth, so along the z-coordinate. We need to write this derivative in terms of spherical coordinates. So to transform from Cartesian to spherical, what we have is the system of equations where in the left-hand side you have the derivatives in spherical coordinates, and in the right-hand side the derivative in Cartesian. You need to apply a Jacobian, this matrix A. The Jacobian matrix is given by, and given the definition of spherical coordinates, the elements of the Jacobian matrix are, what we want is to write the derivative in z in terms of the derivative in spherical coordinates. So what we need is actually the inverse of the Jacobian matrix. If we invert the matrix A, what we have is, so we can finally write the z derivative in terms of the spherical derivatives, which yields, substituting that in the equation of radiative transfer, we arrive at its form in spherical coordinates.